Welcome to a step-in-time chimney sweeps training videos. Today we will discuss how to perform a modified NFPA Level 1 open fireplace masonry chimney inspection. NFPA 211 is a standard created by the National Fire Protection Association for fireplaces, chimneys, vents, and solid fuel burning appliances. There are 3 levels of inspections: Level 1, Level 2, and Level 3. Here, we'll talk about the Level 1 chimney inspection. A Level 1 chimney inspection is the most basic level of chimney inspection and is recommended when there are no changes in appliance or fuel type, and the chimney has been operating under normal conditions. Circumstances: a Level 1 inspection is typically part of your annual chimney maintenance. If you have continued to use your appliance in the same manner as before, and you are not planning on making any changes to the system, a Level 1 inspection is probably sufficient. Scope: a Level 1 inspection is a visual check of the fireplace and chimney without any special equipment or climbing up on the roof. The inspector will look for any damage, obstructions, or buildup that could cause a problem. The inspector will check the readily accessible portions of the chimney exterior, interior, and accessible portions of the appliance and the chimney connection. Degree of access: the inspector will need access to the parts of the chimney that are readily accessible, as defined in NFPA 211 as areas that can be reached for inspection or cleaning without the need for removing permanent parts of the building structure or finish, or without the use of tools or ladders. Circumstances and indications: as stated earlier, a Level 1 inspection is recommended under normal operating conditions, when there is no change in the appliance or fuel type, and when there is no evidence of any problems with the chimney and its operation. This basic inspection will check for damage or obstructions that could affect the performance or safety of the chimney, but it will not involve any dismantling or destruction of the structure. If your fireplace or stove has been working well, and you are not planning any changes, a Level 1 inspection is typically adequate to ensure that your chimney is safe to use. Section 15.2.5 clarifies the extent to which an inspector can exceed the minimum requirements of a given inspection level. Here's what it stipulates. 15.2.5 The following shall apply to examination of the chimney at a level higher than that indicated by Table 15.2.1. 1. Nothing shall prevent the examination of all or part of the chimney at a higher level than the minimum indicated by Table 15.2.1. 2. Partial examination of the chimney at a higher level shall not require that the entire inspection be conducted at that higher level. This section allows for flexibility in the inspection process. The first part states that there are no restrictions preventing an inspector from examining the chimney at a higher level than what's minimally indicated by the guidelines, for instance, a Level 1 inspection. Therefore, if an inspector feels it necessary, they are within their rights to use additional tools, including ladders, and perform tasks typically associated with higher-level inspections. The second part clarifies that even if part of the inspection is performed at a higher level, such as going on the roof or inspecting the chimney from the attic, which are typically part of a Level 2 inspection, it does not mean the entire inspection needs to be conducted at that higher level. This allows the inspector to tailor the inspection to the specific circumstances, needs, and potential hazards of the chimney and its system, going beyond the minimum where necessary, while still classifying the inspection within the level initially determined as appropriate. This ensures a thorough and comprehensive assessment while maintaining the flexibility to respond to specific situations or conditions identified during the inspection process. The ultimate goal is to guarantee the safety and operational efficiency of the chimney and its connected systems. At a step-in-time chimney sweeps, we are committed to providing our customers with thorough and comprehensive chimney inspections to ensure the safety and longevity of your systems. With our unique approach to inspections, we perform a modified Level 1 chimney inspection that is specifically designed to meet and exceed the standards outlined by the National Fire Protection Association, NFPA, 211. Our modified Level 1 inspection may include detailed photographic review of 27 distinct inspection steps. Each of these steps corresponds to specific requirements detailed in NFPA 211A13.3, ensuring that our inspection covers all relevant aspects of your chimney's condition and safety. We understand that NFPA 211A13.3 includes 33 distinct requirements for various chimney and venting configurations. However, we have tailored our inspection process to focus on the 25 requirements that specifically apply to open masonry fireplaces, as not all 33 requirements apply to this particular type of system. By following this approach, a step-in-time chimney sweeps ensures that our inspection is both thorough and relevant, providing our customers with peace of mind, and keeping their open masonry fireplaces safe and operational for years to come. Step 1. Photo 1. Take full-length photo of the front of the house. Please show steepness of roof and if possible, take at the angle that best shows the chimney. This allows us to include these photos in our reports and provides quality control supervisors information concerning complexity of roof access for determining repair estimates. Step 2. Gather information from homeowner by asking a series of questions. 1. How long have you been using this chimney? 2. When was the last time your chimney was cleaned or inspected? 3. Have you noticed any changes in how your fireplace or stove performs? 4. Have there been any recent incidents of fire or overheating? 5. Do you know what type of fuel has been predominantly used in the fireplace/stove, wood, gas, coal, etc.? 6. How often do you use the fireplace or stove during the heating season? 7. Have you noticed any unusual smells or drafts coming from the chimney or fireplace? 8. Do you burn seasoned or unseasoned wood in your fireplace/stove? 9. Have you ever had a chimney fire? 10. Have you made any recent changes to the fireplace, stove, or chimney system? 11. Has the chimney ever been relined or repaired? If so, when and what was the reason? 12. Do you have any concerns about the current state of your chimney or fireplace? 13. Have you ever noticed any water leakage or dampness in or around your chimney? 14. Have you noticed any debris or soot falling into the fireplace or stove? 15. Is there a cap or guard installed at the top of your chimney? 16. Are there any visible signs of damage on the outside of the chimney? 17. Have you experienced any problems with animals or birds getting into the chimney? 18. Are there any trees or buildings nearby that could affect the chimney draft? 19. Do you have carbon monoxide detectors installed in your home? 20. Do you know the history of the chimney, when it was built, any significant changes, upgrades, or previous issues? Step 3. Photo 2. Take a photo that shows the full fireplace opening and 3 feet around the opening. Measure the length and width of the fireplace opening. Multiply the length and width and determine the area. You may notice this requires a tape measure and thus is above the NFPA 211 Level 1 requirement. However, this is very valuable information because it determines the area of your firebox. Pay particular attention for smoke stains above the top of the fireplace. Smoke stains indicate that smoke is backing into the home and the chimney is improperly drafting. Step 4. Measure the distance of the outer hearth from the face of the fireplace. If the area of your fireplace is less than 864 square inches, which is 6 square feet, then the hearth extension needs to project at least 16 inches from the face and 8 inches to the sides. If the area of the opening is 864 inches or more, then it requires the hearth to extend at least 20 inches from the face and 12 inches to the sides. The reason for hearth extensions is to prevent embers from popping onto the floor and the ability to add a freestanding fireplace screen to prevent this occurrence. The hearth extension also adds fire protection to the underside of the hearth extension, which is likely located in the crawl space. A photo of the hearth extension is not required because it is included in Photo 2. Step 5. The fireplace facing needs to project to the sides. The width needs to be at least 8 inches and IRC figure or 1001.11 show it to be 12 inches. This is also a good time to determine your side mantle requirements. Woodwork such as wood trim, mantles and other combustible materials shall not be placed less than 6 inches from the fireplace opening. Combustible material that projects more than 1.5 inches shall not be placed closer than 12 inches from the top of the fireplace opening. Step 6. Photo 3. Take a photo of the fire chamber. This photo should show the condition of the ash dump door, the fire brick, and of the mortar joints. Include an extended tape measure that shows the distance from the front face of the firebox to the rear wall. This distance is required to be 20 inches or more because if it is too short, smoke can back into the home instead of going up through the damper. When you are inspecting the firebox, you may encounter warped ash dump doors, cracked firebrick or deteriorated mortar joints. Ash dump doors typically warp due to thermal stresses on the metal and sometimes from rusting. Firebrick, used for the construction of the firebox, is a type of dense refractory brick capable of sustaining intense heat. The thickness of the firebox walls is required to be at least 8 inches thick. This thickness is important because it can insulate the firebox, protecting the surrounding masonry and other building materials from the heat of the fire. Bricks in fireplaces can crack for a number of reasons, and this is usually due to the stress they experience under heat and time. Here are a few of the common causes. 1. Thermal stress. One of the main reasons that bricks crack is due to the extreme heat they are subjected to when a fire is lit. This can cause the bricks to expand and contract once they cool down, which over time can lead to cracking. 2. Moisture expansion. Bricks are porous and absorb moisture. If water has been absorbed and the fireplace is then lit, the water can turn into steam and exert pressure from within the brick, causing it to crack. 3. Rapid heating. Rapidly heating a cold fireplace can cause bricks to crack. This sudden change in temperature can cause thermal shock, leading to cracks. It's recommended to start with a small fire and gradually increase it to avoid this rapid heating. 4. Improper material. Not all bricks are created equal. Some are more resistant to heat than others. For example, firebricks are specifically designed to withstand the heat inside a fireplace, whereas standard building bricks are not. Using the wrong type of brick could result in cracking. 5. Structural issues. Over time, settling of the house, or other structural issues can put additional pressure on the fireplace and lead to cracking of the bricks. 6. Age and wear. Like all materials, bricks degrade over time. The constant cycle of heating and cooling can eventually lead to small cracks, which grow over time. If bricks in your fireplace have cracked, it's essential to have them inspected and replaced if necessary, as they may pose a potential fire hazard. Cracked bricks can allow heat and sparks to reach potentially combustible parts of the home's structure. Fireplace mortar. Mortar type and size. The mortar used in constructing the firebox is crucial for its longevity and safe operation. The ASTM C199 standard test method for peer test for refractory mortars sets the standards for this type of mortar. Mortar that complies with C199 is designed to withstand the high temperatures within a firebox. The thickness of these joints should be maximum 1/4 inch in thickness. Tight joints decrease the likelihood of mortar deterioration. Fireplace mortar is typically made from a mixture of silica sand, cement, and lime. However, for the extreme heat within the firebox, a special type of high-temperature refractory mortar is often required. This mortar is also known as fireplace, refractory, or heat-resistant mortar. Refractory mortar that complies with C199 has specific properties that make it suitable for use in high-temperature environments. Unlike regular masonry mortar, when refractory mortar is exposed to high heat, it doesn't lose its structural integrity as it cools down. Regular mortar, if used in a firebox, can crack and crumble over time due to the repeated heating and cooling cycles of fires. This is because it expands when hot and contracts when cool, causing it to deteriorate over time. In contrast, refractory mortar is designed to withstand these temperature fluctuations. Step 7. Photo 4. Take photo of the profile seam. This is the inner firebox vertical joint where the fireplace face meets the chimney construction. In masonry, there are 3 types of mortar joints. 1. Bed joint. This is the horizontal joint between courses of bricks. The bed joint is where a mason spreads a layer of mortar as a base where the bricks will be laid. 2. Head joint, also called perpendicular joint. These are the vertical joints where 2 bricks meet side by side. The head joint is filled with mortar after the bricks are placed, ensuring a tight seal between them. 3. Collar joint. This is the 3rd type of mortar joint, which is the space between the inner and outer widths of masonry in a cavity wall. It's filled with mortar to bond the widths together, while still insulating in the cavity. When the mason builds the face over the firebox construction to form the fireplace opening, the mortar joint between these two are considered collar joints. If these joints are not properly constructed, then they can deteriorate and become a fire hazard. Sometimes the mason improperly uses regular mortar instead of the required refractory mortar, and it breaks down from the heat cycles. Step 8, Photo 5. Take a photo of the lintel joint. The lintel joint is the location above the firebox lintel where the front of the damper intersects the inner facing of the top of the fireplace opening. This opening should be filled and sealed solid with refractory mortar. Many times the mason will use regular mortar that deteriorates during heating cycles. This can create a fire hazard because this joint prevents heat from entering behind the combustible mantle. Step 9, Photo 6. Take a photo of the damper. This photo can be of an open or closed damper. If the damper is missing parts, inoperable, or does not open wide enough, then try to document that with a photo. There are basically 3 types of dampers. The most common is a poker damper, and removal of this damper requires removal of a cotter pin. Step 10, Photo 7. Remove the damper plate and take a photo showing the construction of the smoke chamber. Now inspect the smoke chamber. This is the location where there will likely be the highest amount of formed creosote. 1. Preparation. Before inspection, ensure you are wearing safety glasses, including gloves, a flashlight, and a mirror for viewing difficult-to-reach areas. An inspection camera may be useful for detailed examinations. A selfie stick, when properly utilized, can be raised to the highest part of the smoke chamber and can verify there is no blockage or damage in the lower portion of the flue liner. 2. Begin the inspection. With your flashlight, carefully inspect the interior surface of the smoke chamber. According to IRC code R1001.8, it should be parquet smooth with refractory mortar. This surface smoothness reduces turbulence, improves draft efficiency, and prevents the buildup of creosote. Make a note of any rough spots, cracks, and especially if it is corbelled and not parquet. 3. Inspect the slope. Check the slope of the smoke chamber. It should not be more than 30 degrees from vertical for corbelled masonry constructions, as specified by IRC code R1001.8.1. An improper slope can affect the chimney's structural integrity, impact draft efficiency, and contribute to creosote buildup. 4. Examine the height. Next, measure the height of the smoke chamber. According to IRC code R1001. 8. It should not be more than the width of the fireplace opening. An overly tall smoke chamber can decrease draft, increase creosote buildup, and make cleaning more difficult. Conversely, a smoke chamber that's too short violates IRC code R1003.5 regarding corbel projections and can risk the structure's collapse. A too short chamber can also block the draft and redirect smoke back into the home. 5. Check flue liner support. Ensure that the smoke chamber is perfectly sloped to fulfill the requirements of IRC code R1003.12, which states that the flue liner should be supported on all sides. Lack of proper support can lead to structural instability, and smoke and creosote can form on the outer portions of the chimney liners. 6. Final thoughts. A smoke chamber's role in a fireplace is pivotal, as it serves as a conduit to transition smoke and gases from the firebox into the chimney. When properly constructed, the smoke chamber facilitates the Bernoulli principle, which is a cornerstone of fluid dynamics. To understand this principle, remember that an increase in the speed of a moving fluid corresponds with a decrease in static pressure. In other words, fast-moving air has lower pressure than slow-moving air. This principle is crucial for the operation of systems, including the draft in a fireplace. A properly constructed smoke chamber applies the Bernoulli principle to increase draft. 1. Flow constriction. The smoke chamber acts as a transition zone between the large firebox below and the smaller flue above. It gradually tapers, constricting the area through which the smoke and hot gases must pass. This narrowing causes the gases to speed up, like putting your thumb over the end of a hose to make the water spray out faster. 3. Collar joint. This is the third type of mortar joint, which is the space between the inner and outer widths of masonry in a cavity wall. It's filled with mortar to bond the widths together, while still insulating in the cavity. When the mason builds the face over the firebox construction to form the fireplace opening, the mortar joint between these two are considered collar joints. If these joints are not properly constructed, then they can deteriorate and become a fire hazard. Sometimes the mason improperly uses regular mortar instead of the required refractory mortar, and it breaks down from the heat cycles. Step 8, Photo 5. Take a photo of the lintel joint. The lintel joint is the location above the firebox lintel where the front of the damper intersects the inner facing of the top of the fireplace opening. This opening should be filled and sealed solid with refractory mortar. Many times the mason will use regular mortar that deteriorates during heating cycles. This can create a fire hazard because this joint prevents heat from entering behind the combustible mantle. Step 9, Photo 6. Take a photo of the damper. This photo can be of an open or closed damper. If the damper is missing parts, inoperable, or does not open wide enough, then try to document that with a photo. There are basically 3 types of dampers. The most common is a poker damper, and removal of this damper requires removal of a cotter pin. Step 10, Photo 7. Remove the damper plate and take a photo showing the construction of the smoke chamber. Now inspect the smoke chamber. This is the location where there will likely be the highest amount of formed creosote. 1. Preparation. Before inspection, ensure you are wearing safety glasses, including gloves, a flashlight, and a mirror for viewing difficult-to-reach areas. An inspection camera may be useful for detailed examinations. A selfie stick, when properly utilized, can be raised to the highest part of the smoke chamber and can verify there is no blockage or damage in the lower portion of the flue liner. 2. Begin the inspection. With your flashlight, carefully inspect the interior surface of the smoke chamber. According to IRC code R1001.8, it should be parquet smooth with refractory mortar. This surface smoothness reduces turbulence, improves draft efficiency, and prevents the buildup of creosote. Make a note of any rough spots, cracks, and especially if it is corbelled and not parquet. 3. Inspect the slope. Check the slope of the smoke chamber. It should not be more than 30 degrees from vertical for corbelled masonry constructions, as specified by IRC code R1001.8.1. An improper slope can affect the chimney's structural integrity, impact draft efficiency, and contribute to creosote buildup. 4. Examine the height. Next, measure the height of the smoke chamber. According to IRC code R1001. 8. It should not be more than the width of the fireplace opening. An overly tall smoke chamber can decrease draft, increase creosote buildup, and make cleaning more difficult. Conversely, a smoke chamber that's too short violates IRC code R1003.5 regarding corbel projections and can risk the structure's collapse. A too short chamber can also block the draft and redirect smoke back into the home. 5. Check flue liner support. Ensure that the smoke chamber is perfectly sloped to fulfill the requirements of IRC code R1003.12, which states that the flue liner should be supported on all sides. Lack of proper support can lead to structural instability, and smoke and creosote can form on the outer portions of the chimney liners. 6. Final thoughts. A smoke chamber's role in a fireplace is pivotal, as it serves as a conduit to transition smoke and gases from the firebox into the chimney. When properly constructed, the smoke chamber facilitates the Bernoulli principle, which is a cornerstone of fluid dynamics. To understand this principle, remember that an increase in the speed of a moving fluid corresponds with a decrease in static pressure. In other words, fast-moving air has lower pressure than slow-moving air. This principle is crucial for the operation of systems, including the draft in a fireplace. A properly constructed smoke chamber applies the Bernoulli principle to increase draft. 1. Flow constriction. The smoke chamber acts as a transition zone between the large firebox below and the smaller flue above. It gradually tapers, constricting the area through which the smoke and hot gases must pass. This narrowing causes the gases to speed up, like putting your thumb over the end of a hose to make the water spray out faster. 2. Pressure decrease. According to the Bernoulli principle, as the velocity of the gas increases in the constricted area of the chimney flue, the pressure decreases. This drop in pressure is what creates a suction effect, also known as a draft. 3. Air movement. The lower pressure in the chimney flue compared to the firebox draws the smoke and hot gases upward and out of the chimney. Simultaneously, it pulls in fresh air from the room into the firebox or from fresh air intake tubes if installed, which is essential for proper combustion to occur. 4. Optimized draft. With a perfectly constructed smoke chamber, the transition of smoke and gases from the firebox to the chimney flue is smooth, reducing turbulence and maintaining a high velocity of gases. The result is a strong, steady draft that effectively vents the byproducts of combustion from the fireplace. In essence, a properly constructed smoke chamber leverages the Bernoulli principle to maintain and enhance the draft, enabling the fireplace to operate efficiently and safely. Any obstruction, rough surface, or incorrect slope in the smoke chamber can disrupt this process, leading to poor draft, smoke spillage, or other operational issues. Step 11. Photo 8. Take a photo of the smoke shelf. A smoke shelf is an essential part of a masonry fireplace that serves multiple functions. A hollow smoke shelf or one improperly constructed can lead to several issues that compromise the operation and safety of the fireplace. A hollow smoke shelf can accumulate creosote in this hollow cavity and can cause a major chimney fire if this creosote ignites. This can lead to nearby combustible material to catch fire. Hollow smoke shelves are very dangerous. On the other hand, a smoke shelf constructed with an upward curve and filling in behind the back wall of the firebox serves several important functions. 1. Enhances structural integrity. A solid masonry smoke shelf contributes to the overall structural integrity of the firebox and the fireplace system as a whole. This additional support can help to prevent the fireplace from deteriorating over time, thereby extending its lifespan. 2. Redirection of downdrafts. The upward curve of the smoke shelf helps to redirect downdrafts back up the chimney flue, keeping smoke and other combustion byproducts out of the home. 3. Capture of falling debris. An upwardly curved smoke shelf can also act as a trap for falling debris from the chimney. This includes not only natural debris such as leaves or bird nests but also chunks of creosote or loose bits of masonry that can pose a risk if they fall into the firebox. Figure 1001.1 in the International Residential Code, IRC, provides a general diagram of a fireplace and chimney, but it has been criticized for not accurately representing the proper formation and placement of the smoke shelf. In particular, the image seems to depict the smoke shelf too high above the firebox and does not adequately illustrate the damper in the front of the smoke chamber. This can potentially lead to misinterpretations and may lead to the construction of hollow smoke shelves. Step 12. Photo 9. Take photo of exterior clean-out door. An ash dump clean-out door and a smoke chamber clean-out door in a fireplace each serve different purposes and are typically different in size due to these different functions. 1. Ash dump clean-out door. This type of door is designed to provide access to the ash dump, a compartment located beneath the firebox, so that ash and other debris can be removed easily. The size of these doors can vary, but typically, they are smaller since they only need to accommodate ash and smaller pieces of debris. 2. Smoke chamber clean-out door. The clean-out door for the smoke chamber is usually larger than an ash dump clean-out door. It provides access to the smoke chamber, which is the area above the damper and immediately below the flue where smoke is collected before being expelled from the chimney. Due to the increased potential for creosote buildup, a highly flammable byproduct of wood burning, these doors need to be larger to accommodate the tools required for thorough cleaning. In terms of code requirements, under the International Residential Code, IRC, R 1003.17, masonry fireplaces, clean-out doors must be installed and accessible for both the ash dump and the smoke chamber. They must be tight-fitting and constructed of approved, non-combustible materials. They are required to maintain the integrity of the fireplace and chimney, reduce the risk of accidental fires, and facilitate regular maintenance and cleaning. However, the code does provide an exemption stating that clean-out doors are not required where cleaning is possible through the fireplace opening. This means that if there is sufficient access through the fireplace opening to clean the smoke chamber and smoke shelf, then a separate clean-out door isn't necessary. This often applies to traditional masonry fireplaces. The exemption, though, usually doesn't apply to most steel-form fireplaces because the damper and tubes can block direct access to the smoke chamber and smoke shelf. These types of fireplaces are constructed with different materials and design features that can obstruct thorough cleaning through the main fireplace opening. Therefore, a dedicated smoke chamber clean-out door is typically necessary. Step 13, Photo 10. Take a photo of the exterior side of the smoke chamber. The rear wall of a masonry fireplace smoke chamber is required to be 6 inches thick and coated with refractory mortar for several reasons. 1. Thermal efficiency. The 6-inch thickness serves to provide better thermal efficiency. It reduces heat loss to the exterior and keeps the chimney warmer, thus promoting better draft. 2. Structural stability. A 6-inch thick wall offers more stability and strength. It is better able to resist the stresses induced by the heat and gases produced during combustion. 3. Safety. This thickness also adds a layer of safety, reducing the risk of fire spreading from the smoke chamber to adjacent materials. 4. Protection from thermal shock. Coating the wall with refractory mortar, a heat-resistant mortar, adds an additional layer of protection against heat and thermal shock. Bricks are made from ceramic materials, which are good conductors of heat but have poor tensile strength. This means that when the inside of a brick in the smoke chamber wall heats up during combustion, it expands, while the outside of the brick, which is exposed to cold outside air, remains cooler and does not expand at the same rate. This temperature difference and the resulting uneven expansion can lead to vertical cracking of the bricks. This is a phenomenon known as thermal expansion. These vertical cracks could be potentially mitigated by proper mortar joint construction. If the mortar joints were constructed with Type N mortar, which is known for its medium compressive strength and good resistance to weathering, the mortar might be more prone to cracking rather than the bricks. This is because mortar is typically designed to be weaker than the bricks so that it will fail first under stress, thereby protecting the bricks. However, often the rear wall of the smoke chamber is not constructed to the code-required 6 inches in thickness, but instead is made only 4 inches thick. This reduced thickness amplifies the issue of thermal expansion, leading to more pronounced and potentially more frequent cracking, as the thinner wall is less able to resist the stresses caused by the heat and provides less thermal insulation. This might also lead to higher heat loss to the exterior, reduced chimney efficiency, and potentially more safety risks. Step 14, Photo 11. Take a photo of the general condition of brickwork of the chimney. Pay attention to defects like brick spalling, cracked brick or separated mortar joints. Brick and mortar joints play a critical role in the durability and functionality of a masonry chimney. Over time, exposure to various environmental conditions can lead to degradation of both these components, impacting the chimney's overall condition. One common issue with brick is spalling, a process where the surface of the brick peels, pops out, or flakes off. This often happens when the brick absorbs moisture, which then freezes during colder temperatures. As the water freezes, it expands, exerting pressure on the brick and causing parts of it to crack and break off. This freeze-thaw cycle can be especially problematic if the mortar used isn't Type N. This mortar is known for its durability, flexibility, and good resistance to weathering, making it ideal for exterior applications where it may be exposed to these cycles. The separation of the mortar from the brick is another common issue and can occur due to a variety of reasons, such as improper installation, using the wrong type of mortar, or simply age and wear. This can create gaps that allow water to penetrate the chimney, potentially causing leaks during rainstorms. To help preserve the life of the brick and mortar, different types of masonry water repellents can be used. These products work by creating a barrier that prevents water from penetrating the brick without blocking the pores of the brick or mortar. This allows moisture trapped inside the masonry to evaporate, preventing damage from freeze-thaw cycles and minimizing the potential for leaks. Another consideration for a masonry chimney is its ability to withstand lateral wind loads and vibrations from earthquakes. These forces can cause a chimney to sway, creating tension and compression that can lead to separation of the brick joints. Over time, these movements can cause the joints to open, compromising the structural integrity of the chimney and potentially leading to leaks or even collapse. Chimney shoulders refer to the areas of a chimney where it tapers or steps in, usually from a wider base to a narrower upper section. There are two primary methods of constructing these chimney shoulders, each with its own unique set of considerations. 1. Corbelled brickwork. In this method, the bricks are stepped inward at each level to gradually reduce the size of the chimney, forming the shoulder. While this approach is visually appealing and can offer a traditional aesthetic, there are a few challenges. Brick holes can potentially allow water to enter the chimney, leading to water damage. To mitigate this, each level of corbelled brickwork should be coated with a layer of mortar or a mortar parch. This creates a smooth, water-resistant surface that prevents water infiltration. However, over time, the mortar can degrade due to environmental exposure, potentially allowing water to penetrate. 2. Overlay with solid masonry pavers. The second method involves using corbelled masonry to form the basic shape of the chimney shoulder, but then overlaying this with solid masonry pavers. This method can offer a smoother, more uniform appearance and, because solid pavers do not have holes, there is a lower risk of water infiltration through the brickwork itself. However, the mortar joints between the pavers can still be vulnerable to water penetration and degradation over time. Regardless of the method used, it's important to be aware of potential issues with mortar degradation. Over time, environmental exposure can cause the mortar to deteriorate, potentially leading to leakage into the chimney shoulders. To help protect against this, you should consider applying a masonry water repellent. These products create a barrier that prevents water from penetrating the mortar and bricks, without blocking their pores. This allows any moisture that does get in to evaporate, reducing the risk of freeze-thaw damage. Over time, small cracks or gaps may develop in the mortar, and catching these early can prevent more serious problems down the line. If you notice any signs of damage, it's important to repair them promptly to prevent water infiltration and potential damage to the interior of the chimney. Step 14, Photo 11. Take a photo of the chimney flashing. Chimney flashing is an essential component in ensuring that the connection between your chimney and roof is watertight. It serves as a seal to prevent water from entering your home at the point where the chimney penetrates the roof. There are two primary types of flashing involved in this process. 1. Step flashing. Step flashing consists of a series of rectangular pieces that are interwoven with the shingles and bent to fit up against the side of the chimney. Each step is layered over the one beneath it to direct water away from the chimney and towards the shingles, where it can run off the roof. 2. Counter flashing. Counter flashing is designed to work with step flashing to provide an extra layer of water protection. It is embedded into the chimney masonry and bent down to cover the top of the step flashing, creating a continuous seal that prevents water from seeping behind the flashing. The use of riglets can improve the effectiveness of counter flashing. A riglet is a groove cut into the brickwork into which the top edge of the counter flashing is inserted. The flashing is then sealed with an elastomeric sealant, a flexible, waterproof sealant that expands and contracts with temperature changes and building movement. This helps to prevent water from entering between the brick and the flashing. An ice and water shield is another layer of protection that can be applied under the shingles around the chimney. It's a type of self-adhesive membrane that sticks directly to the roof decking. This shield provides an extra barrier against water penetration, particularly useful in colder climates where ice dams can form and push water back up under the shingles. Over time, the flashing can rust and leak, particularly if it's made from a ferrous metal like steel. Regular maintenance, including rust prevention treatments and resealing with elastomeric sealant, can help extend the life of your flashing. However, if it becomes too corroded or damaged, replacement might be necessary. It's also important to note that if riglets are not used, a common occurrence in some constructions, the reliance on the elastomeric sealant to seal the flashing increases. If this sealant dries out or weathers, it can cause leaks. Regular inspections and maintenance, including reapplication of the sealant as needed, can help prevent this issue. Proper installation and regular maintenance of chimney flashing is critical to prevent water damage to your home. A chimney cricket, also known as a chimney saddle, is a small, peat diversion structure built behind chimneys that protrude through sloped roofs. It is designed to divert water and snow around the chimney, preventing it from accumulating at the chimney base, which could lead to leaks and water damage. IRC Code R 1003.20 stipulates that chimney crickets are required on the ridge side of any chimney greater than 30 inches wide, as measured perpendicular to the slope. This code requirement is in place to help ensure that chimneys don't create obstructions on the roof that can trap water or debris, leading to moisture problems or roof damage. The absence of a chimney cricket on chimneys wider than 30 inches can lead to several problems. 1. Water accumulation. Water can pool behind the chimney, increasing the chance of leakage. Over time, this can result in water damage to the roof, the underlying structure, or even the interior of the home. 2. Snow accumulation. In colder climates, snow can accumulate behind the chimney, and as it melts, it can seep into the roof, leading to similar water-related damage. 3. Debris accumulation. Leaves, branches, and other debris can accumulate behind the chimney, potentially leading to damming and further water issues. This debris can also create a fire hazard. Even when a cricket is installed, problems can arise if it's not properly constructed or maintained. Issues like improper sizing, incorrect slope, or poor waterproofing, like improper flashing or sealant application, can compromise the cricket's effectiveness and potentially lead to water or debris accumulation. A chimney crown is a critical component of any chimney structure, providing a first line of defense against weather damage. As the topmost element of a masonry chimney, it sheds water away from the chimney, protecting the structure below from water penetration. According to IRC Code R 1003.9.1, chimney crowns must be constructed in accordance with ASTM C 1283, which provides specific guidelines for their construction. Here are the primary requirements. 1. Thickness and overlay. The chimney crown must be a minimum of 2 inches thick at its edge. It also needs to extend at least 2 inches beyond the exterior chimney wall, forming an overhang or drip edge. This overhang helps to direct water away from the chimney structure, reducing the risk of water damage. 2. Slope. The crown should slope at a minimum of a 10-degree incline away from the center of the chimney to the edges. This slope helps to direct water runoff away from the flue and off the crown. 3. Bond break. The crown should be separated from the flue liner by a flexible, caulked bond break. This bond break allows for independent movement between the crown and the flue, reducing the likelihood of cracking due to thermal expansion or structural shifts. 4. Flue liner extension. The flue liner should extend at least 2 inches but no more than 4 inches above the crown. This helps protect the crown from high heat and directs flue gases and sparks safely away from potentially combustible materials. 5. Reinforcement. The crown should contain a reinforcing mesh embedded within it. This mesh can help increase the structural strength of the crown and resist cracking. These specifications, while they may sound technical, essentially create a chimney crown that has a better chance of withstanding the elements and the test of time. It forms an effective drip edge that protects the masonry below and helps prevent water infiltration, which is the most common cause of chimney deterioration. Despite these established guidelines, many existing chimney crowns do not conform to these standards, primarily due to a lack of awareness or understanding of their importance. However, modern chimney sweeps are becoming increasingly aware of the benefits of this type of construction and are adopting these methods to improve the durability and performance of the chimneys they service. Adopting these practices can significantly enhance the lifespan and safety of the chimney structure. A chimney cap, also known as a spark arrestor, serves a crucial role in the overall function and safety of a chimney system. It prevents sparks from escaping the chimney and causing potential fire hazards, while also keeping out rain, snow, debris, and animals. Furthermore, it helps to maintain proper chimney draft, which is vital for effective combustion in the fireplace or heating appliance. Regulations around chimney caps are outlined in both NFPA 211 and IRC R 1003.9.3, with each stipulating requirements for the net free area of the cap, which is the total area through which air and combustion gases can escape. 1. NFPA 211 4.6.4.1. This code requires that the net free area of the chimney cap or spark arrestor should be at least 3 times the cross-sectional area of the chimney flue outlet. 2. IRCR 1003.9.3. According to this code, the net free area of the chimney cap should be at least 4 times the area of the chimney flue outlet. In the case of a discrepancy between these two codes, the strictest one would apply, meaning that a chimney cap would typically need to comply with the IRC code and provide a net free area at least 4 times the size of the outlet. For multi-flue chimneys, NFPA 211.4.6.2 provides additional guidelines. If the chimney cap extends above the tallest flue tile, the distance it extends should be at least the smallest dimension of that flue. For example, if the flue outlet measures 8 inches by 8 inches, the cap would need to extend at least 8 inches above the flue tile. Additional requirements state that the mesh should not allow passage of a sphere with diameter of 1/2 inch or block the passage of a sphere of 3/8 of an inch. These guidelines are in place to ensure a proper draft in the chimney and minimize the risk of dangerous sparks escaping, while also allowing for adequate ventilation and protection against weather and animal intrusion. Inspect the chimney liner. Begin your inspection by examining the joint between the top flue tile and the second flue tile. A gap might be present due to thermal expansion that occurs when the chimney is in use. This can occur because the heat forces the top tile through the crown, and friction prevents it from returning when the liner cools down. Proceed to inspect the rest of the chimney liner. Use a bright flashlight to illuminate the interior of the chimney. You're looking for signs of damage or deterioration, such as cracks, gaps, and even hairline cracks because they expand when heated. Document the damage. If you find any damage, take clear pictures for documentation. Use the flashlight to ensure sufficient light for the photos. Damage assessment. Compare the damage you find with the guidelines in the NFPA 211 section 14.9. This section states that any damaged or deteriorated liners should be repaired or replaced. Final photos. You have completed your modified masonry chimney inspection, but you should check other portions of the home to prevent future damage to the home. This can be unsealed exposed roofing nail heads, rusted vent pipes, leaking in deteriorated vent boots, and finally you should check to see if the dryer vent requires cleaning. This concludes our modified NFPA 211 Level 1 chimney inspection. Thank you for watching.